did in this demonstration today in a little bit more detail, or rather not in detail. We're going to sum up what we did, and then we're going to go over the practice questions in a bit of detail. So if you weren't here in class, we did a demonstration where we took some water that was tinged with a little bit of universal indicator. And so this neutral water had a greenish tinge to it. And so our neutral water kind of was like had a green tinge. And we also took some of that water in another flask, but I added a bit of hydrochloric acid. As you can see, there's a slight difference in color because we have an indicator, a pH indicator in here. That just changes color when we change the acid or base concentrations. All right, and so we get this color difference as a result. And so the acidic flask was kind of an amber. In the video, it seems to look a little yellow, but sort of an amber. I'm just going to call it yellowy. Or I like amber, actually. We're going to call it amber. Okay. And we had this flask C. Now, initially, it was the same identical flask, had the same contents as our neutral flask. And that was until we had people blow with a straw into their flask. And when they did, actually some of the color has gone from this flask. So I'm just going to grab a new straw to maybe bring out some of that color again. And as we see, by adding or breathing into the flask, we get a really different color from this neutral color, that green. We get so breathing into this flask seems to change the color, much more similar in nature to this acidic flask here, and that's our acid flask. And so by breathing in carbon dioxide, we were able to turn this flask to an amber. And that was similar to the acidic flask, which we just got by adding some hydrochloric acid. And our green, well, we didn't do anything to our green, so our neutral flask stayed green. So what do we take from this? We take that by breathing into water, exhaling into water, I should say, we're able to change the color of a pH indicator inside the water. And as a result, what does that reflect? It reflects a change in acid in the water. So we talked a little bit about this reaction from a perspective of Le Chatelet's principle, which says, okay, so the reaction here is carbon dioxide and water. And I'm going to leave a little space here because we're going to have an energy argument in a bit. And as it lives in equilibrium with a substance called carbonic acid. And we should probably add phases here. This carbonic acid is an aqueous phase. Water is a liquid. And this carbon dioxide, well, I think, discussion, like you can make an argument that there's a gas and then it turns into an aqueous. I think I'm going to argue that it's aqueous for now. And I'm going to regret that later, and I know why. But if it's aqueous, it means we're blowing a gas in, and then under another Le Chatelet's principle argument, more gaseous carbon dioxide creates more aqueous carbon dioxide. Now, so, and in addition, it turns out this is an endothermic reaction. This isn't going to be important for our immediate thoughts, but just happens to be true. It also takes in about 40 kilojoules of energy from the system. All right, so anyway, we're trying to break our dynamic equilibrium thought process into some formal steps. And so what we were doing, is trying to break these Le Chatelier's principal ideas into some steps. And so we started by saying, okay, well, what change was introduced into the system by us breathing into it? And the answer is that we increased the amount of carbon dioxide. Okay. And equilibrium wants to minimize that change. That's Le Chatelier's principle. So to undo an increase, it's going to try to decrease carbon dioxide. I drew a smaller arrow to imply that it won't completely diminish that change, but it will minimize it. So what direction will equilibrium shift so as to minimize that change and decrease some carbon dioxide? It wants to decrease the amount of carbon dioxide. Okay, well, let's look back at the reaction here. If we want to decrease carbon dioxide, well, carbon dioxide is a reactant. So if this reaction takes more reactants and turns them into products, that will diminish the carbon dioxide concentration as a result. And so it will push this reaction, shift it toward the products. So just to reiterate that, we introduced a change, which is we increased the carbon dioxide concentration. These little square brackets mean concentration. The equilibrium wants to minimize this change by decreasing the carbon dioxide concentration. And to decrease the carbon dioxide concentration, it's going to combine it with some water and form carbonic acid. So it's going to shift to the products. What's the result? Well, this extra, we have an increase in our carbonic acid. And that causes an increase in the acidity of a solution. Now, where does this happen? This happens in the oceans. So we're experiencing climate change from an increase in carbon dioxide in the atmosphere. And so just like when we bubbled carbon dioxide through water and we found that it made it more acidic, more yellow like an acid, well, this happens in oceans. The more carbon dioxide in the atmosphere means more carbon dioxide in the water, and that forms more acid. As a result, the pH of the ocean is dropping as the acid becomes more acidic. And this is a problem for shellfish, for coral reefs, and actually those are the two that I'm aware of. I imagine there's probably other ocean creatures that this affects that I am unaware of. All right. But really what I want to do is I want to make sure we can make it through each of these questions by looking at how this reaction can change. Okay. So, question 1. I do not think there's enough space to write out all your thoughts. I would encourage you to use another piece of paper. Okay. So, for question 1, what if we added more carbonic acid? What direction would equilibrium shift? Okay. So I think it's important for us to break this into a series of steps. So what change did we introduce? Okay, we introduced by adding carbonic acid, we increase H2CO3. Okay, so what's the second question we need to ask? Well, what does equilibrium want to do to minimize that change? So, what does equilibrium want to do? To minimize, this change. Okay, well, it wants to decrease the carbonic acid concentration, right? Okay. So which direction will equilibrium shift to decrease this product? If you want to decrease a product, you want to take that product and form some reactants out of it. So if you want to decrease this concentration, you're going to shift toward the reactants. It's going to shift toward the reactants. So I'm going to write that as a sentence. Equilibrium will shift toward the reactants to decrease H2CO3, the carbonic acid concentration. Okay. Question 2. What if we reduce the amount of water in the solution to make it more concentrated? Okay, I'm going to step aside for a second. I'm going to grab an eraser. I'm going to do some of his thoughts on a whiteboard. All right. So question 1, what change was introduced? Going back to the question, we reduce the amount of water in a solution to make it more concentrated. So what if we decrease the amount of water? So we're decreasing H2O concentration. Okay. We decrease the amount of water. So I'll just write down what change. We decrease the amount of water. How will equilibrium minimize? Well, it wants to increase the H2O concentration as a result. And which direction will it shift to increase the water concentration? Well, if we look at the reaction, if we want to increase the water concentration, well, we're going to do that by shifting products, decomposing them to make more reactants to increase that water. So this shifts equilibrium to the reactants to increase the concentration of water in our solution. All right. So what if we added even more carbon dioxide? So what change will occur? Well, it's going to obviously increase carbon dioxide even more. How will equilibrium minimize this? It'll do so by doing the opposite. It decreases carbon dioxide concentration. And then lastly, how's equilibrium going to shift to make this happen? Well, we want to decrease carbon dioxide, and if I look back at the reaction, I see that carbon dioxide is a reactant. If I want to decrease the amount of this, I got to shift equilibrium to the products, combining these two together to make some products. So that means equilibrium shifts toward the products to decrease CO2 concentration. All right, moving on. Look at question 4. Question 4 asks, well, what if we increase the temperature? All right, so what's changed? Is introduced? Well, we're going to increase the temperature. And so to minimize LCP, the Le Chatelier's principle, is to decrease the temperature. Okay, so to decrease the temperature, we have to recognize this is an endothermic reaction. Endothermic. And this reverse reaction is exothermic. Now, one of those is going to be able to decrease temperature when it proceeds. Which one? Well, endothermic reactions decrease temperature. They suck up energy from the surrounding system and they store it in the form of chemical bonds. So the endothermic reaction, the forward reaction, pushing the reactants toward products, is going to take up some of that energy and reduce the temperature. So we're going to find that equilibrium shifts to the products to minimize temperature. Okay. Question 5, and we're going to leave it at question 5. And that's because we talked about aqueous carbon dioxide and not how gaseous carbon dioxide plays a role. So we're going to look at question 5 and talk about a decrease in temperature. So what's the change? What change is introduced? Well, that's a decrease in temperature. So how are we going to minimize that? Using Le Chatelier's principle? Well, that means we'll increase the temperature if we can. And to increase the temperature, that means we need to go the exothermic direction, taking products and forming them into reactants to release that energy, that 40 kilojoules for every mole we have, back into the system. So equilibrium is going to shift to the reactants to increase the temperature. All right, and we're going to call it there. Now, because we looked at the aqueous form of carbon dioxide, we're going to be unable to detect any difference in terms of equilibrium if we increase or decrease the pressure. All right, so we'll call it there. Let me know if you have any questions about that.